Welcome to Pre-Calc, Lesson 2.4, the last section or last clip. Earlier in our learning, either in class or in video, you looked at using the rational root theorem to find all possible rational zeros and determine which are zeros. You learned to solve polynomial equations and to solve for those zeros, not just plug them in to find out if they're zeros. You learned to write the factored form of a polynomial equation both in irreducible form and in linear form. And you learned how to write a function given the roots. We're going one step further with that, where you're given a root that is a complex root. So you'll have to build at least that part, or one of the irreducible factors from the root that's given, so that you can find all complex zeros and write a linear factorization when given a root. That is today's target. Zeros of polynomial functions. We are expected to be able to, once again, the learning target, find all complex zeros of the function, and then write the linear factorization of the function. Here is a function that's given, and it's a function that I have to give you one of, at least for now, one of the complex zeros, because there are no rational zeros for this function. So you won't be, rational roots theorem will not help you. All of the factors of 58 divided by the lead coefficient of 1 will not produce any zeros. They're all irrational and or complex, that they may have imaginary parts. So knowing or given that this one is a zero, I need to find its irreducible factor to divide away from this polynomial function. So I start with the equation x equals 2 plus or minus 5i. Now if you like doing this with the conjugate pairs as you learned in Algebra 2, you may start with x equals 2 plus 5i and x equals 2 minus 5i, and get your three trinomials to multiply from that. I'm not going to do it that way, but you're welcome to. Some of you prefer that method. With this one, I'm going to subtract 2 from both sides. I'm now going to square both sides, because that's what they did that gave us the plus or minus 5i, was they took the square root. When I square positive or negative, it comes out positive. 5 squared is 25, and I squared is I squared. On the left, I have x squared minus 4x plus 4 if I expand this as x minus 2 by x minus 2. I squared is equivalent to negative 1, so this is 25 times negative 1. Giving me x squared minus 4x plus 4 equal to negative 25. To find the complete factor of this, I have to get it equal to 0. So the irreducible factor that gave us this 0 and its complex conjugate was x squared minus 4x plus 29. That is the irreducible factor. I cannot do synthetic division for nonlinear factors and irreducible factors like this. So I'm going to have to do long division. But I know that this should go in evenly, giving me a remainder of 0, assuming that I built this equation correctly. So I'm going to make sure I don't have any missing terms, and I don't, so now I'm just going to copy down the equation and make sure that I can do the long division. So this first part right here, this was our first step, building the irreducible factor that we can now divide away. X squared times x squared gives us x to the 4th. X squared times negative 4 gives us negative 4x cubed, and positive 29x squared. I'm going to have to change the signs on every term, giving me negative 2x cubed plus 6x squared minus 50x minus 58 when I bring down those last terms. To multiply to negative 2x cubed, I have to multiply this, or this, by negative 2x, giving me negative 2x cubed plus 8x squared minus 58x. Change the sign, combine like terms. I get negative 2x squared, that's not right. Yes. Plus 8x minus 58. Well, all I have to do is multiply these by 2 to get this, so I'm going to do plus 2, which gives me, or sorry, not plus 2, minus 2, which gives me negative 2x squared, plus 8x minus 58. And when I change the sign now, they're all opposites, I get my remainder of 0. So we now have our irreducible, we took this irreducible factor and divided it out. What's left is this. The linear factorization, well, it's not linear, but the factorization of these would be this. That which we built and that which we just found by division. This one, it's 0 and its complex conjugate. They're right there. This one, I have to find it. It is not factorable. That's why I wouldn't be able to use rational root theorem for this. So to get the zeros for this one, I have to do the quadratic formula. Opposite of b over 2a plus or minus the square root of b squared minus 4 times a times c, which is the square root of 12, over 2. This gives me 1 plus or minus, 12 is 4 and 3, so 2 square roots of 3 over 2, 1 plus or minus the square root of 3. There are my remaining zeros. I was asked to find all the complex zeros. Well, there's 2, 1 was given, right? And its complex conjugate also is included, so it's 2 plus or minus 5i. So there are all 4 roots for this 4th degree polynomial, this quartic equation. 2 plus 5i, 2 minus 5i, 1 plus square roots of 3, 1 minus square roots of 3. Now, to write the linear factorization, again, I get these equal to 0, but I'm going to do them one at a time, so I would subtract 2 and subtract 5i. I would subtract 2 and add 5i. Here I would subtract 1 and subtract square roots of 3. Subtract 1 and add square roots of 3. That's a minus 1, not a plus sign. So there's my 1, 2, 3, 4 linear factors. Here are my irreducible factors, giving me these zeros. 1 was given, giving me these zeros we found after doing the long division. And then getting these equal to 0, we get our linear factors, doing them one at a time. I'm going to give 2 more examples of this. In the second example, this is again, we're finding the complex zeros, so assuming there are no rational zeros. I'm not sure why there's an equals 2. I think it was just supposed to end there. Oh, it should say x. Yeah, there we go. X equals 2 is 0. So if that's the case, then x minus 2 equals plus or minus the square root of 3. We're going to build our irreducible factor. We know that 2 plus square roots of 3 and 2 minus square roots of 3 are some of the answers. So I'm going to square both sides. It's going to give me x squared, because that's x minus 2 by x minus 2, equals plus or minus square roots of 3 squared. So x squared minus 4x plus 4, plus or minus squared is just positive, and then the square root of 3 squared is 3. Subtract 3 from both sides. My irreducible factor is x squared minus 4x plus 1. It's one of my irreducible factors. We're going to divide that. That'll be our divisor. Our dividend is x to the fourth minus 10x cubed plus 35x squared minus 46x plus 10. X squared times x squared is x to the fourth. X squared times negative 4 is negative 4x cubed. X squared times 1 is positive x squared. I'm going to change the sign on everything. That's gone. Negative 6x cubed, positive 34x squared minus 46x plus 10. To get to this to be x, so negative 6x cubed, we have to multiply by negative 6x, giving us negative 6x cubed, positive 24x squared, negative 6x. I'm going to change the sign on everything. This one goes away. We're left with 10x squared minus 40x plus 10. To get to 10x squared, we need to multiply by 10, positive 10, giving us 10x squared minus 40x plus 10. When we change the signs, we get a remainder of 0. So this is our other irreducible factor right here. Our other irreducible factor is x squared minus 6x plus 10. The zeros that came out of this one, we already knew. They were told to us. So it was x equals 2 plus square roots of 3, and x equals 2 minus square roots of 3. This one I have to solve using quadratic formula. So I have the opposite of b over 2a plus or minus the square root of the discriminant over 2a. A is 1. I'm going to do b squared minus 4 times a times c, which is negative 4. So that's going to become 2i over 2, and that's going to become 3. So I have x equals 3 plus I, and x equals 3 minus I. These are my zeros. We were asked to find all of the complex zeros. There they are. We were also asked to write it in terms of linear factorization. So this one gives me x minus 2 minus square roots of 3 times x minus 2 plus square roots of 3. This one gives me x minus 3 minus I, and this one gives me x minus 3 plus I. There's the same polynomial function written as linear factors, the product of linear factors. One last example of this. Here's our fourth degree polynomial. We're told that x equals negative 3i. So that means that x also equals 3i, but I'm going to start with x equals plus or minus 3i. When I square x, I get x squared. When I square this side, plus and minus are dropped, I get 9i squared. But I is negative 1, so I actually get x squared equals negative 9. The reason this is not factorable, when I add 9, I'd have x squared plus 9 as the irreducible factor. I'm going to divide the x squared plus 9 as the divisor into the dividend of x to the fourth plus x cubed minus 3x squared plus 9x minus 108. To multiply to x to the fourth, we need to multiply by x squared. X squared times 9 is 9x. I'm missing an x term, so I have to do 0x. So that'll be 0x cubed and plus 9x squared. Change the signs. This gives us x cubed plus 12, or minus, not plus, minus 12x squared plus 9x minus 108. Continue dividing. To multiply to x cubed, we multiply by x. X cubed plus 0x squared plus 9x. Change the signs. we have negative 12x squared plus 0x minus 108. To get to negative 12x squared, we multiply by negative 12, negative 12x squared plus 0x minus 108. When we change our signs this time, we get a remainder of 0. So one of our irreducible factors was x plus 9. We built that off of this given complex 0. The other irreducible factor is x squared plus x minus 12. I don't know that that is irreducible. X minus, or x plus 4 by x minus 3. We were asked to find all the zeros. Maybe this one is reducible. So this would be negative 12, positive x, negative 1, or negative 3, positive 4x minus 3x is 1x. This one is factorable. I get x equals negative 4 and x equals positive 3. They gave me one of the complex zeros, and I was able to get the two that are actually also complex, but they're also real numbers and rational numbers. So the other ones came from x equals 3i and x equals negative 3i. There's all of the zeros listed. In terms of the factors, we have x plus 4, x minus 3, by x minus 3i, by x plus 3i. This concludes the video examples for how to divide out, if you're given a complex zero, how to build the irreducible factor, divide it out, and solve the remaining equation. Have a great day.